Thank you all for making the time, especially this early in the morning. So the title of my dissertation is Human-Inspired Control for Robot Interaction with Complex Objects. And to start, I'm going to show you something you probably already know, and that's that humans can perform amazing feats, from juggling a soccer ball or juggling small balls with each other, throwing axes, or moving across a slack line. Now I will show you something you may not already know. My lab mates also perform amazing feats. They can collaboratively move a table together. They can drink coffee while talking without spilling it. They can swing on a swing. And of course, the last one is Vani tying her shoelace with a blindfold on. Now, you may not agree that these activities are impressive, but roboticists definitely do, because they constantly try to compare the performance of their robots to humans. As you can see from these examples, comparing to the average human by making robots more human-like, and lastly, even admitting that the technologies in robotics currently doesn't even match human-level performance. And that's why this is the world that my research is focused on. I've placed a heavy emphasis on the human first, and I tried to study how humans interact with robots and other complex objects. And with that, the chapters in my dissertation are, in the first chapter, I study humans physically interacting with a robot. And here the robot has a fixed trajectory. And so the human has to follow the robot path. There is no degrees of freedom for the human to control. In this study, we realized a need for a good grip sensor or a grip force measurement device that doesn't currently exist in the human motor control field. And so in chapter 2, I designed such a device and built it. And subsequently in chapter 3, I implement this device in a new project while also increasing the complexity of the object the human interacts with. Here we have a 1 degree of freedom object, whereas with the robot, it was a fixed path with no degrees of freedom. Here we study how humans manipulate such a 1 degree of freedom object. And the next step would be to increase the complexity, maybe a double pendulum. But given that there is a research in our lab studying how humans manipulate whip, and that was an interesting project to me, I decided to go even more complex and study how humans manipulate a 25 degree of freedom underactuated object that looks like a whip. And then lastly, I plan to implement this controller I designed on robots in order for robots to manipulate such complex objects as dexterously as humans as well. So in chapter 1, I'll focus on physical human-robot interaction, where a human has to follow a robot trajectory. A bit of motivation. Traditionally, robots have been isolated from humans, placed in rooms, and whenever a human enters their space, they're programmed to shut down immediately. More recently, the human-robot interaction has allowed humans and robots to at least share the same workspace, but still, they don't share the same task. It's almost like the human, for example, here, places the screws and moves on to a different part while the robot does its job. The next step to that is physical human-robot interaction. This adds even more complexity for tasks such as cutting a piece of wood together, given the heterogeneity of the motor control of the human and the robot. With that, we argued that the control of the interaction forces is critical for successful physical human-robot interaction. In a recent study by Pauline, she showed that human force control is actually better when the robot trajectories exhibit human-like behavior. And the way human-like behavior is defined is using the power law, where the velocity v scales with the radius of the curvature, r, with the power exponent beta. And with this equation, if you set the beta to 1/3, what you get is a human-like trajectory, or how humans would move along a curved trajectory. A follow-up study to that by West et al. From a collaborator group, showed that human force control can also not be decoupled from the robot motion. And so with these two studies, the questions I try to answer is, can humans learn to improve their interaction with a robot that doesn't follow the power law? Secondly, if we provide them with visual feedback, does that help them improve their interaction with the robot? And then lastly, can humans overcome this inherent limitation in the force motion coupling that exists? With these questions in mind, we designed 3 velocity profiles using that power law. The first one is the biological, and let me just get my pointer. Okay. First one is biological, which follows the power law, and you can see here the tangential velocity, the trajectory, the movement is slower along the curved parts and faster along the straight parts. The second one is what we call constant, where we set the beta to 0. So this is a constant tangential velocity profile. And last one is exaggerated, which is basically an exaggerated version of the power law, where the robot would slow down even more along the curved parts and speed up even more along the straight parts. And just to give you an idea of what this experiment actually looks like, here I am doing the task. So it's a planar motion with the robot, and the participant gets a real-time feedback of how well they're doing. I can also show you the same trajectories in terms of angular velocity, and this will become important later on, but the top row and bottom row are the same trajectory, just shown as tangential or angular velocity. And so with that, the task instruction to the participant was to firmly hold the robot handle and trace the ellipse with the robot while trying to minimize the force you apply to it. And of course, one way to do this task perfectly is to just let go of the robot, because you're not going to exert any force. And that's not what we wanted. We want them to firmly hold the handle. At the time, we didn't have a good grip sensor. So what we did was place a force sensor resistor as sort of a binary check, at least to make sure they're holding the handle. We can't tell how firm they're holding, but at least they're holding it. Before we look at the actual results, just to give you an idea of what the force patterns of that the participant exerted on the robot looks like, here's 3 representative subjects, and the force vectors are shown, starting from the right-hand side, going around and coming back. It's already clear that participants are exerting very different forces across these 3 velocity profiles. And the performance metric I will use to evaluate their performance is the root mean squared of the force they apply in each trial. So the question I wanted to answer here is, again, from Pauline's work, we know that humans prefer to interact with a robot that exhibits the power law and don't do as well when it's violating it. So the question we asked here is, what if we let the participants practice for multiple days? Can they learn those non-intuitive, non-biological velocity profiles? And in summary, what we see is participants who received visual feedback were able to improve their performance. And we actually had an equivalent cohort of participants who were blindfolded while doing the task. And so they had to rely on their haptic and proprioceptive senses to figure out if they're tracking the robot well or not. And we actually don't see any improvement there. And lastly, for participants who interacted with the robot that followed the power law, perhaps not surprisingly, we don't see any improvements. And this is because, well, the power law itself is a human-inspired trajectory, and humans are already comfortable with that motion. So with that covered, the next question was the force and motion coupling. So we hypothesized or asked the question, okay, does the human applied force depend on the trajectory's curvature, the tangential velocity, or perhaps the angular velocity? And if you recall this figure I showed earlier, from this figure alone, we can start to answer some of these questions. Because the first question is it dependent on the trajectory's curvature? In the biological, constant, and exaggerated, we have the exact same curvature, same ellipse, yet we see very distinctly different force patterns across the 3 velocity profiles. So the force applied does not only depend on trajectory's curvature. What about tangential velocity? Well, remember that I said in the constant case, the robot is actually moving at a constant tangential velocity. So if force depended on tangential velocity, we should expect to see a consistent pattern across the ellipse for the constant case. But we do not see that. And so this leads us to think that the human applied forces cannot just depend on tangential velocity. And the last one, for angular velocity, what we do first is to split the force applied into its tangential and normal components. And the vertical gray lines you see are one ellipse. So these are repetitions of the elliptical motion. And even visually, it's clear to see there is consistent modulations per ellipse. And so what I did next was to plot these forces versus at each time point versus their corresponding angular velocity, which is what you see here, both in tangential and normal force, plotted against the corresponding angular velocity. I calculate the median across all the trials, which is the dark black line, then fit a linear regression to this data, which is the two lines you see here, and do the same thing for all participants. And already you can see a consistent behavior, especially across normal force for this group. And I ran the same analysis for all the participants across different groups, and we see the same behavior, which leads us to say that yes, human applied forces do depend on the angular velocity. All right, coming back to the overview, so far I showed the importance of considering the human and what the human prefers when a robot is interacting with a human, and that human-like motions are preferred. And the second thing I showed was limitations in how much humans can adapt their behavior. The other key thing was the need for a grip sensor. I used the FSR in this study, but that's not a good measure of how much grip force the participants are applying. And so in chapter 2, I designed, Peter has a question. Yes.
Yeah, my question is about when you're talking about the different velocity profiles and trying to understand what affects human performance.
Mm-hmm.
Is that all considered in the sort of the tool frame, like the end effector frame, or do you consider looking at human motion in terms of their own joint coordinates?
So this is at the end effector space, but the idea of power law is also has been shown in the end effector space. So if you ask participants to trace clover shapes in space, their movements follows this power law as well.
But I think, Peter, do you mean in joint space, for example?
Right. I'm just wondering if it's more appropriate to draw correlations in the person's own joint space or in the end effector space.
Yeah, so from the human motor control side, there are some studies that show humans do planning, motion planning at the joint space level. But more recently, there are more studies showing that humans actually plan it at the end effector space. And what you're saying is correct, that like we could also look at the joint space. But for this project, we focused on the end effector space because ultimately that's the connection point between the human and the robot. So from a robot side, the robot should only really needs to worry about what the human likes at the point where they touch each other, not what the robot's joints do to achieve that.
Right. I mean, I'm just a person that, from an intuitive perspective, which is, my own comfort is related to my joint motions.
Mm-hmm.
So I would guess that you'd find correlation for joint motions and for end effector motions. I was just curious if there was a sense of which was stronger.
Mm-hmm. Go ahead, Dagmar.
No, you, Maddie.
There's definitely got to be correlations because it's the joints that lead to the end effector motion. The one other thing I'll say interestingly from this experiment is if you ask participants to trace this ellipse at a constant speed, they do the power law. They don't do the constant tangential velocity. So even when we think we're moving at a constant speed, we slow down around the curves and speed up along the straight parts. Rifat, I think, has a question as well, but yeah, Peter. Okay.
I have a couple of questions for myself to better understand. So these results are based on providing visual feedback.
These are, but if we run the same analysis so there were two groups of participants, those who received visual feedback and those who didn't. The results I show here are for the ones who receive visual feedback. The reason we did that is because one of the questions we want to ask is, does this limitation exist throughout? Because if you remember from the previous results I showed, participants in the non-biological group who received visual feedback showed a significant improvement in their performance. So we wanted to ask, okay, somehow they're reducing the force they're exerting on the robot. Could it be that they're overcoming this limitation in their motor control system? Now, it could be biomechanics or many other things, but the question was, is this like, are they sort of adjusting the slope here to make it flatter, and that's how they're exerting less force? And we see that no, this limitation still exists. And I don't show the results here, but if you compare the slopes for first few practice trials versus the last few, which is what I show here, the slopes are not significantly different. It's just that they're slightly shifted. So they don't overcome the limitation. They just learn to overall reduce less forces.
What do you mean by non-biological subject?
So if the velocity profile of the robot followed the power law with the exponent beta equal 1/3, we call that biological. And the idea basically is that if you set the exponent to something else, you're kind of violating the power law or the biological motion. And that's why maybe I interchangeably call the constant and exaggerate non-biological or non-intuitive to humans.
Mhm.
Yeah.
And here you strike with red H1 and H2. But I was wondering why not maybe the force is a composite decision of the three together. Maybe not one alone, but all three combined together maybe can improve your correlation effort. Why not?
That's a good point. One of the things also I'll say is the study I cited by West et al. Earlier in the introduction that showed a coupling between force and motion.
Yeah.
Kind of kept it at that level. They're like, oh, force seems to be coupled to motion, and not actually digging into it and figuring out what about the motion is it that the human force is coupled to. And that's what really inspired this study. And that's why we wanted to kind of go in and try to see if we can find one kinematic metric that best explains this force and motion coupling.
Okay.
But there's definitely it could be a combination of these and perhaps other parameters that we have not fully considered here.
Yeah. And how did you choose the angular velocity range here in the color bar? So how was that determined?
So the way it's determined is first we had to, for example, for the biological, decide how long we want the period of this path to be, which we set to 3 seconds. So for the biological, it takes 3 seconds to start from here and go around and come back. And so that tempo is what determines the angular velocity for the other two. Basically, follow a constant tangential velocity here, but do this whole path in 3 seconds. Same thing with this one. Follow the exaggerated profile, but do it in 3 seconds. And that's how we get the angular velocity or tangential.
You fix the period to back solve the speeds.
Exactly.
Okay. Thank you.
Sure.
But maybe just responding to the ideas that come from Rifat and Peter. So it could be an interesting variation to modify the period. We have Pauline has previously modified the orientation of the ellipse, but didn't find any changes, any differences in the force behavior. But what we haven't done is to change the overall period such that what we regard currently are velocities in a human preferred range may be pushed into slight more extremes. I think that could be interesting to test that. And maybe also, as I'm taking note of ideas, what Peter said, that this, say, undesired forces and effort that might arise in the human-robot interaction could be easily evaluated in joint space. That the whole power law issue in human motor control has only been examined in endpoint space. So that's why we sort of implicitly focused on that.
Yeah.
And I think these are all very good points to consider in moving forward.
Yep.
I'm sorry, maybe I may ask one more question. Are these ellipses in the world corner frames in the sense that the person is drawing an imaginary ellipse on the wall? Or have you rotated these ellipses in some way that they look horizontal in their larger axis?
I can go back. So here we go. So this is the
on the
actual
wall.
task. What they see is on the screen. So this is for participants who receive
Mhm.
visual feedback, but
Yeah.
the path is like parallel to the ground.
Got it.
Yep.
The reason I'm asking is, and is this the most comfortable way of drawing an ellipse for the individual, given the kinematics of our forearm and its limitations in terms of the angles it can produce? Is this the most comfortable ellipse one can draw, or if it was tilted, would it be easier? Anyway, it's just a question, but you made a choice here and you want to be consistent with the literature, so this obviously makes sense. But I was just wondering, are there some inherent challenges for the individual to be able to produce this perfectly horizontal ellipse?
So two points. One, just to make sure it's clear, the robot is programmed to draw this ellipse. So if I were to release my hand, the robot would still trace that ellipse. So
Okay.
that's one thing. And the reason perhaps we don't do a frontal ellipse is because there you also have to do gravity compensation, and that just adds unnecessary complexity to the question we are trying to ask here. But as Dagmar said, one other aspect of Pauline's study was to basically rotate the ellipse 90 degrees so that the long axes are in front of you as opposed to your sides. And in that study, Pauline did not see any significant difference in the forces participants applied.
Okay, thank you.
Sure. I will go ahead really quickly. Okay, so chapter 2, designing a new grip force sensor. And I will explain, but the goal is to estimate human arm stiffness using this grip force. Firstly, why do we need a grip force measurement device? One reason is to enhance the research in human motor control and human-robot interaction. As an example, here's an experiment where the participants is interacting with a robot, and you can see they're holding the handle and primarily interacting through that handle. Knowing how much grip force the participant is exerting there could give us more information about their control strategies and control behavior, but it can also be used as a control knob for the participant. So for example, if they're, moving a cup of coffee using the robot, they can, if they grip the handle harder, then maybe the trajectory will move faster, or things like, you can basically use it as a control knob to control different things. The next reason is it's a grip force is a good proxy for arm stiffness. Why do we need arm stiffness, or why do we care about arm stiffness? In the field of human motor control, this is typically how the human upper limb is modeled, as a two-link system. And the stiffnesses are usually estimated in separate studies where they perturb the human arm to try to estimate what the stiffness is. But of course, this is a constant value that everyone, most people in the field have just used in their models. But more recently, studies have shown that you can actually use grip force to get a better and real-time estimate of those stiffnesses. So here you can see the stiffness ellipsoids at the end point of the human arm. And the lighter the color gets, the higher the grip force the participant was exerting. And so we can see a relation between grip force and human arm stiffness. And this is something where I'm actually going to exploit in the next chapter. But lastly, beyond my own research and human motor control and robot interaction, it has grip force measurement has applications in the health sector as well. There's research that shows a connection between grip force and cardiovascular health, severity of Parkinson's disease, and motor impairments in post-stroke. So applications for such a device can go beyond just scientific research in motor control. All right, where are we right now with grip sensor devices? The state of the art right now is the Jamar hand dynamometer, which is on the left. This is used in hospitals and clinics as well. A lot of competitors have come in with similar designs, making slight improvements to the existing design, such as the Grippable or the K-Force Grip. These devices have limitations that includes, first and foremost, being limited to uniaxial force measurement. And by that, I mean that you need to apply grip force it can only measure your grip force in one direction along its sensing element. But that's not how humans apply grip force around the cylindrical handle. We apply radial forces to squeeze radially into the handle. These devices will not be able to accurately measure that. Second one is they're mostly limited to measuring the maximum grip force. So they're designed to be able to have high operating ranges, but not good at measuring lower forces. And lastly, they are all very expensive. So here is our proposed solution. First, I'll talk about what it does and how it works, and then how it works. So firstly, our device can radially sum the grip force applied, meaning that if you look at here, meaning that you can apply grip force at the bottom here, at the top here, or anywhere along these load plates. And I will show you results that it can accurately measure those grip forces. It is not limited to maximum grip force. We're able to accurately measure grip force anywhere between 1 Newton to 200 Newton. And it's a cost-effective way of building a grip sensor. We showed the bill of materials in the submitted paper, and it costs less than $20 to build this entire device. And lastly, because our goal was for other researchers to be able to use this and build one for themselves, we ensured that it's easy to build and use. Now, how does the device actually work? Here you can see a cross-section of it. These are thin flexures, and this whole sensor body is actually 3D printed, including the flexures. And the way these flexures work is they restrict the motion of the light blue load plates in sort of a horizontal to the plane that we're seeing here, and forces these two central cores apart from each other. And because of these flexures, it means that if you apply 5 newtons here or here or here, they result in the same separation of these two central cores. And that's how we're able to accurately measure grip force anywhere along the cylinder body. So let's first see if the device actually works well. So the first thing is to calibrate it. And I use an instrument machine to calibrate the grip sensor. Here you can see the results of the calibration. We get a pretty low error, root mean square error of 1.5% of full scale, which is 200 newtons, and very high linearity. Next thing to consider is hysteresis for sensors like this, which is basically if you load up the sensor and unload it, how different are the measurements from the device at the same force levels. And the maximum hysteresis we see in our device is 1.4% of full scale. Next one, which is the new contribution of our device, is to radially measure grip force. So here, the first thing I do is I apply 100 newtons of force on the center plate. So I have a device here. If this is the whole device, I apply 100 newtons along the center of it using an instron, which also has its own load cell, which I show in red. And then I apply the similar amount of force along the two far edges of the device, which is the second half you see here. And then I can compute the difference between the instron and the grip sensor to get an estimate of the error. And you can see that compared to the 200 Newton operating range that we have, we're only getting around 1 Newton of error at both of these locations. And so we're able to relatively accurately measure grip force wherever it's applied along a load plate. But what about the different load plate pairs? Because there is 3 pairs radially arranged next to each other. And so what I do next is I apply 100 newtons along one pair and then rotate the device, apply 100 newton along the next one, and so on. And here also we can see similar performance as before, around 1 Newton of error for a 200 Newton operating range. The next thing was to make it easy for people to build this device. And so what I did was I recorded a 20-minute tutorial going step by step, showing how this can be done. Rifa, do you have a question?
So there are 3 pairs of these components around the circumference, and the individual is squishing a pair at a time. That's the assumption.
So you don't need to be squishing them at a time, because the way the design works is it radially sums. But the way I showed it is to show that if you apply forces to them one at a time, how different is the output? Because there could be imperfections in the 3D printing, for example, that may make it that one pair of load plate is slightly stiffer. But we show that those imperfections from 3D printing is not significant enough.
Okay.
Yeah.
And how much of grip force do you anticipate from the subjects, plus minus?
That's a good question. So just for people to know, the maximum grip force humans could apply varies quite a bit, but it's around 500 newtons. So larger than the operating range of our device, but our goal was never to go to the maximum grip force. This is more for human motor control and robotics applications. And I can tell you that like if you were to just hold this handle as loosely as you can, you're probably applying 5 to 10 newtons. And if you try to squeeze it pretty hard, you will go around like 150, 160. If you squeeze it really hard, yes, you will max out the sensor. But for the applications we have in mind, the 200 Newton was more than enough range for it to work.
And in the next slide, did you also test at lower newtons the percentage of error? 100 is obviously a good number to start with, but did you check where the device starts to become unreliable?
So the nice thing about the load cell I use, which is basically a strain gauge, is as you can see here, so those black dots are me applying that much force. So for example, here I applied 20 newtons of force for 60 seconds. And you can see how well the grip sensor would be able to estimate. You can see it's pretty much on the line. And so that's the nice thing about this sensor is that the behavior is fairly linear, especially up to 200 newtons. In the paper we submitted in the supplementary material, we showed that when you go beyond 200, it starts to become nonlinear. The device still works up to 360 newtons, but because for the applications we had in mind, we didn't even need to go to that high of a level. We chose to keep it within the linear range where it's easier to calibrate as well.
Got it. And in the right-hand side of the slide, you said you apply 100 newtons. And so that is Instron reading is your ground truth?
Yes. That is an assumption we make. And again, we have the values, but the Instron load cell is fairly accurate. I think it's 0.005 newtons.
I thought you had another independent force measurement system, but looks like Instron is your ground truth, which is fine. Okay.
Okay. Oh, let's go back. So yeah, created a video showing how to build a device, and of course open source everything on GitHub. The code, the CAD files, even all the data we collected during the experiments. So the next thing was to show an example of this device working in a human motor. Yes, Pauline?
So just a question. I was wondering whether you tested how the characteristics of the device changed through time. Because I mean, it's also 3D printed materials, and I guess that if you use that a lot, maybe like the curves that you show, I mean, basically they change. And I was wondering whether it's something that you tested or not. It's more like for if people want to use that, do they know if they have to reprint the parts regularly or something like that?
Yeah, so in the paper we've submitted, we don't discuss that. And that's something we're planning on doing a little bit more. So like finite element analysis on it and things like that. But to answer your question from my own experience, the device that I ran these tests on, I printed a year before I ran these tests. And I was just using the same device across all the tests I had done. So there'll definitely be fatigue over time. But in my experience, and like in my test, I tend to push it pretty far. I never had it fail when I was using it correctly. The easiest way to make these things break. So if I go back to the design, the key difference between our device actually and other existing devices that look like this is we have a steel rod that connects the two ends together, which is what transfers the load to the load cell. If you forget to include that steel rod in here, it will if I squeeze this just hard enough, I can break it because the steel rod is not there. So that's typically been the way these devices have broken in the past, where like I show it to someone and they squeeze thinking, oh, it's a grip sensor device, so it should be able to work. And if it's just like this, they can easily break it. But if you put that central rod, what it does is it prevents the flexures from bending beyond their limits. And so you don't get breakage. And that's actually more detail. This was inspired by a different study, but because they didn't have the central rod, they had to use thicker flexures in their study. Thicker flexures affects the sensitivity of the device. So ours is actually more sensitive because we use that central rod.
Thank you.
Sure. Okay, so
Rifat's
Yes.
hand is up.
Yes, Rifat.
Maybe since Pauline asked about the lifespan, maybe I should ask another sensor characterization question.
Mhm.
Did you do any dynamic characterization, like oscillatory forces at different frequencies, and then check how the sensor responds?
That's a good point. No, I did not do that. I can look into that. Yeah, I mean, I've done that like with my hand, but I haven't done it with the instron, which is what we should do, because to have a ground truth. So yeah, that's a good point. I will look into that. Thank you. Okay, so for showing the device actually working in human motor control studies, first we do a force only task. So what you will see is this path will scroll across the screen, and there is this blue cursor here. I will control the vertical position of that cursor with my grip force. So if I play it, you will see I'm right now squeezing harder, lowering my squeeze and changing. This is task, we collect the participant data with it, asking them to keep the cursor in the path. The next experiment was a more human-robot interaction where the human actually had to move the robot to do the task. Here, I control both the horizontal and vertical position of the cursor, vertical still being with my grip force, horizontal being with actual movement. And so from these two experiments, just to give you an idea of what the force pattern or the movement of the cursor looked like for each participant, we had 3 difficulty levels, and that was defined based on the thickness of the path on the screen. In the previous slide, I showed you the medium level. So there is one level easier with a thicker path and then one level harder with thinner path. And you can see how the participants did here. And we can quantify the error relative to this path of the Euclidean error of the cursor to this path, and calculating the error in the 2 experimental conditions where they only had to modulate their grip force or modulate their grip force with movement. We see a clear change in performance as the difficulty level increases. And so this is mostly an example to show that this device can be used in human motor control and robotic studies as a good measure of changes in participant performance. Okay. Next, my overall goal in my PhD research has been studying humans manipulating complex objects. In chapter 1, it was a robot, but the robot had its own predefined path. So the human almost had no degrees of control over the object. In the next part of my research, I wanted to give humans a degree of control. And so that's why I studied humans manipulating a pendulum. On top of that, we had this new grip sensor that we could use in this study as well to measure participant grip force. So in chapter 3, I will study human interaction with a 1 degree of freedom object, exploring the role of stiffness through grip force in human object interaction. So the motivation, this is the experimental setup we have in the lab. Participants are asked to swing a pendulum at their preferred frequency. And we have 2 different pendulums, a short one and a long one with different oscillation periods. If we look at what the participants did or what period the participants were swinging these pendulums in the long case and the short case, we can clearly see that when they're interacting with the 2 pendulums, they adapt to the object's dynamics. And by that, I mean the natural frequency or the natural period. And that's because if you see in the long pendulum, the frequency they chose is around the natural frequency. And the moment we switch over to the short pendulum, they adjust their swing frequency to get close to the natural frequency of the system. The reason this is interesting is because they didn't have to do that. We told them swing it at your preferred frequency. They could have been swinging the pendulum at any frequency, yet they seem to recognize what the object naturally wants to do as well. Yes, Rifat.
Mahdi, why do you think they like to swing it at the object's natural frequency?
So that's one of the sort of like underlying points of my research is that when humans interact with an object, especially as roboticists, we tend to think the human controls everything, the human dictates the dynamics. But this is an example of showing that even with a simple pendulum, the humans adjust their behavior based on what this pendulum naturally wants to do. Why do they want to do it? Well, one of the obvious reasons may be that this minimizes the amount of work you need to do because you're not fighting against the pendulum. You're letting it move with its natural dynamics. Pauline?
Yeah, so I think my question is quite close to Rifat's question. But the first thing is, did you have some instruction about performance, which could, what exactly were the subjects instructed or asked to do?
So the participants were asked to, so this is part of a larger study. The instruction was to swing the pendulum at your preferred frequency, but we have other conditions on top. First one is you just sit there and you swing the pendulum. And this is I should say, this is a work by Helene, who is in the call as well. I'm sort of helping and bringing my grip sensor into it more than the actual experiment. But you tell them to swing it at their preferred frequency. The next experimental condition is you actually ask them to count backwards by 7 from like a number in the hundreds. And so the idea here is how much does increase in cognitive load impact your swing frequency as well. So to say that the fact that they adjust their swing period to the pendulum is not a new thing. It's papers back as 90s also have shown this. So that's like, this has been shown already. What we're digging deeper into is what could change this behavior, especially in what Helene's looking at. Like, if you count backwards, does that adjust the frequency you swing at because you further want to offload the motion to the dynamics of the object because you're busy counting? And the other one she does is doing algebra, basically adding two numbers together. Again, just keeping the brain occupied and distracting them from the object. And what we see there is, yes, it definitely impacts their behavior, but it's not always that they get closer to the natural frequency of the pendulum. And that's where the grip sensor could also come in, as I'll explain in the next 2 points.
And just out of curiosity, well, I don't know if it makes sense, but did you, because you're talking there about like people could swing the pendulum at their preferred frequency. Did you, or would it make sense to also try with some kind of imposed frequency that would deviate from their preferred frequency, also having it with and without cognitive load to see, like, maybe, I don't know, would your, maybe if you deviate a lot from the preferred frequency or for the natural frequency, plus if you add cognitive load, then it really starts to get complicated. Well,
maybe Helene can comment. I can't currently think. Maybe, I don't know, Helene, do you know if other studies have used a metronome?
So with the pendulum swinging, I'm not aware of a study that used the metronome to control for the period, but I would guess that during cognitive load, you come back to the natural frequency of the pendulum.
Yes.
Because you minimize effort and you're busy doing something else. Maybe one thing to specify as well is that we ask participants to have a good grip on the handle.
Yes.
To be able to study stiffness. But the question is, when you're doing cognitive load, are you offloading to the natural frequency of the pendulum, or are you actually squeezing more because of the stress of the cognitive load in a way?
Yeah. And one other thing I'll say, Pauline and others as well, one of the challenges we have here, there is like some ideas we have of like improving the experiment. One of them being like, how can we instruct a certain swing amplitude? But the challenge remains that because the participants are like looking at a screen and counting backwards or doing math, any other demands they may just ignore. You know, we could put a metronome there, but they may just ignore it because they're so busy counting, or like put markers on like, we need you to swing up to this height. So that's also a challenge. So one of the things we're, for example, thinking of doing is having a few trials in the beginning as sort of familiarization, where we kind of give them an idea of like, hey, this is the period we want you to swing it at, and this is the amplitude. And hopefully the participant will try to stick to that as best as possible. But during the experiment, especially with the cognitive load, it's hard to give them more information.
So let's go to what you actually want to do here. And
Okay.
I'm concerned about the time because all these additional manipulations were not exactly your point, but another one which you should present now.
Yes. Okay. So the other thing to note here is while they adjust their behavior, they maintain a consistent deviation from the natural frequency. For example, this red participant was swinging faster, and they continue to swing faster even when they do the short pendulum. And so this is where we're looking to see, can variations in the wrist stiffness, which we can measure through grip force, explain these user preferred tempos. And why do I say that? It's because this is how we model the pendulum and the wrist. So the wrist is a torsional spring with a stiffness that the human controls, because this is our wrist stiffness, and we swing the pendulum. If I show you, so this is an actual experimental data of participants swinging the pendulum. This is the pendulum angle. With the grip sensor on the device, we can measure their real-time grip force as well, which you see in orange. So you can see some modulations in grip force. Now, because we have a model of the system, we can back calculate the torque needed to actually drive the system along this path. And remember, the torque should come from the spring. So if I plot the estimated torque in blue, we see a similar, again, this is preliminary results, but we see a similar pattern where there's a higher peak after a smaller peak. One other thing to mention here is, and this is a challenge with any grip force measurement device that is for object interaction, is when you're applying the force you're applying to the handle is not just your isometric grip force, it's also force to translate the object. And whatever grip sensor you use will also measure that force as part of it. And so something that both Helena and I are working on, and Rack is also working with a different project to disentangle, is the isometric grip force removed from the translational forces. Yes, Peter.
It looks like these grip forces are very small down into the sort of accuracy and resolution range of your sensor. Is that something that you're concerned about?
Yeah, so these are, maybe I should say, very preliminary results. We're working on improving the setup as of next week. The grip sensor here wasn't calibrated to the, so I printed a new one for Helen because the one I was using is on Rack's project. So this device is not actually calibrated. So we had a meeting yesterday about it. Just from my intuition of having used these devices for a year or two, the forces applied are twice or three times more than what this device is outputting. This is just preliminary, like with the calibration factor I had from the other device putting it in. But to answer your question, the forces are higher. And one other thing we plan on doing is instructing the participant to exert a certain amount of grip force. And we can actually, if the idea is that grip force and stiffness are correlated, then if we tell them to grip harder, that means their stiffness should also go higher. Yeah. Okay. So in chapter 3, I studied humans interacting with a 1 degree of freedom object, no underactuation. A next step would be to maybe go study humans interact with a double pendulum. A project in our lab working with Alexei is studying how humans manipulate a bullwhip, a flexible bullwhip. And so I sort of ramp up the complexity to get closer to a real bullwhip. And this is where I study humans interacting and manipulating a 25 degree of freedom underactuated whip. So interaction with an underactuated object, designing a human-inspired controller to manipulate the whip. A little bit of background. Here's a video of a human manipulating a flexible object, and you can see I actually had to slow it down for us to truly appreciate what's going on. In contrast, this is the state of the art in robotics, where the video is sped up 4 times, the robot manipulating a cable, and it still looks very slow to us humans. So my goal is to learn from humans to manipulate flexible objects. And this is the study I mentioned by Alexei from 2 years ago, studying how humans manipulate a bullwhip to hit a target. Inspired by this, I model and design a 25 degree freedom whip modeled using Euler-Lagrangian formalism. And I give participants this whip and I ask them to hit a target. And one thing I'll note here is that this is a 2D whip, so there's no 3D motion. You have to do motion along the plane. But this was just to simplify the problem a little bit to make it feasible. So from the participant experiments, we saw two strategies show up. One was what we call striking, where you only make a forward motion to hit the target. That's on the left. And the second one where they make this backward preparatory motion before hitting the target. And we also have the motion capture data for these. That's how we analyze the kinematics of it. And what I did was develop a human-inspired controller. Having observed humans do these two strategies, we designed a controller that tries to mimic those motions. And we use minimum jerk, which is a well-established idea in the field of human motor control, to design these two trajectories. So here I'll play the two strategies, trying to hit the same target, which is shown in black. Striking only is one minimum jerk motion, and preparing and striking combines two motions. So you move the whip back and then try to hit the target. And just from these two examples, you can already see with one motion, the target cannot be hit. With two motions, it can be hit. And just to mention that this is in simulation, so an optimal optimization was used to find the right parameters for these trajectories to hit the target. Yes, Pauline.
Just to make sure I understood correctly, the minimum jerk trajectory that you're doing is the hand trajectory, right?
Yes.
Okay.
Um,
I mean, I feel like though minimum jerk has been used a lot, but I don't. I don't know how much it's been used for manipulating this kind of object. So whether you wanted to show that minimum jerk can extend to also manipulating underactuated object, or whether it's something that's already been shown and that's why you chose this trajectory.
So to answer your question, in a way, this is new, and in a way, it's not 100% new. So, and it actually goes back to your previous question. In a previous work by Moses and our lab, Moses used minimum jerk to design joint trajectories of a human-like arm, so a two-link arm, and a two-link arm with shoulder, elbow, and eventually I think he had a wrist. So Moses has done something similar to this to do planning at the joint space level, only in simulation. Yes, Rifat. Sorry, yes.
Just very quickly, did you do, because I saw like people it seemed that someone has done mocap on that. Did you look in terms of like, if you have motion capture data, can you look at for example, at the hand trajectory or whatever trajectory and check whether the actual trajectory of participant follow minimum jerk principle on this kind of manipulation or not?
So these are the trajectories of the two videos I showed you. And Pauline, to your point, so this is the way we do it to make it simpler was we basically calculate the angle of the arm, okay? And so here's the angle of the arm for striking, angle of the arm for preparing and striking. And ultimately, you should look at the angular velocity to get that classic bell curve. And you see that very clearly here. We haven't fitted a minimum jerk trajectory to these yet. That's something we're thinking of doing. But this was more a human-inspired control. So this looks like a one sub-movement, which is a word you're probably familiar with. And here you see two sub-movements, one moving back and one moving forward. So this is what we saw that led us to think, okay, a minimum jerk trajectory may work.
Okay.
But just watch your language here. It's not very clear because the minimum jerk trajectory is a symmetrical bell shape thing, and there is a very clear deviation from it. Clear is a relative word.
Yes.
So it's not as near as given, and it's an approximation, which is your first step into doing this.
Yep. Rifat, you had a question?
What do these x, x2, z2 mean below the equations?
Sure. So ignore the bottom row for now. If you just look at the top row, this x and z determine the xz coordinate of the end effector, or the whip handle, let's call it. And what's on the right-hand side is a simplification of minimum jerk. So if you pick where you're starting in x, where you're ending up in x, so in x space, and this is a normalized time, basically how quickly you want to get there. If you know where you're starting, if you know where you're ending and how quickly, this equation designs a minimum jerk trajectory, which basically the velocity follows a bell-shaped curve. And so I do that for X, I do that for Z. The top row gives us the trajectory on the left. And then for the one on the right, we have two movements. So this moves us backwards, and then this will move us forward to hit the target. And all of the value, well, all of them. Everything you see in color here, we use pattern search to find the optimal value with the goal of the tip of the whip hitting the target.
And in both cases, these coefficients 6, 15, and 10 they end up being the same.
Yes, these are fixed to get the minimum jerk. Yeah.
Okay.
Okay. So here we kind of got a hint of why participants may be using that extra backward motion, because even in this example, for this target position, with just a forward motion, we weren't able to hit the target, but with a backward motion, we were able to hit it. And so I wanted to dig deeper and see if this is really there. So what I do is a grid search. And the way you can think of this grid search is as if we pretend like there's a target at every single one of the squares in this large rectangle I show here. We run the optimization to try to get the tip to hit the target, and we see how close we were getting by the end of the optimization. The color tells you the Euclidean distance. And so the dark blue down here, this means that for these target positions, the tip of the whip hit the target when we're doing a striking only motion. If I do the same thing for the additional preparation motion, this is what we get. And overlaying them makes it clear why participants may be doing this extra motion. So the dark green is target positions that only the two sub-movement or the preparing and striking strategy was able to hit. And so this shows that humans have a reason for making this extra motion, which adds to the complexity of their trajectory because it helps them hit the target. All right, so in chapter 4, I designed a human-inspired controller to manipulate whips in simulation. The next step and the ultimate goal is for a robot to do this task as well. And that's what I propose in chapter 5, robots manipulating this whip to hit a target. So the only slide I have on this.
One
yes.
quick question.
Yes.
Sorry, one quick question. Are you measuring grip force when they're doing the planar whip?
That's a good question and a good point. So the grip sensor I've been working on for a while, but only as of a month and a half ago has been submitted. So I am working on getting that going. It will definitely be part of it because it's a fairly straightforward addition to add the grip sensor to the whip handle and study how humans basically modulate their grip force. The challenge there still remains, as I maybe hinted at earlier, to separate the isometric grip force from the forces needed to just move the whip. Hopefully, because we have a relatively accurate model of this 3D printed whip, we can calculate the torque and the forces needed and remove it. But that's where I think the real challenge will come in for truly measuring the grip force. Yeah. All right, so very preliminary results. Yes.
But just to emphasize, I think if nothing else, for the consistency of your work, as well as for the just scientific value, what you can get out of this very project, you should absolutely do that.
Yep. I wrote it down. It is in the plans as well. So
yeah.
All right, this is the only slide I have on this because it's very preliminary and I'm curious to hear your thoughts as well. On the left, I'll show you a trajectory in simulation where the modeled whip can hit a target. Now, if I implement a similar trajectory on a robot, can we get it to work? And this is very preliminary, but seems promising. I implement that trajectory on our haptic master robot and it's hitting the target. So my ultimate goal would also be to show that this works on different robots. So we recently got a Franca robot arm. So I'm hoping to program that as well to hit the target with the whip. But again, this is very preliminary. There's still a lot of work that needs to be done to modify the controller from the previous chapter to get it to work on a robot. But with that, we've come full circle. walk through all the chapters, and now let's just revisit my claim from very early on that my lab mates can perform amazing feats. So the video on the top left is in the realm of what I worked on in chapter 1. This here is a human and human interacting together. In my study, it was a robot and a human, where the robot had a fixed trajectory and the human only was adapting. Here, both my lab mates are adapting to each other, so that's one difference. But in chapter 2, I discussed the importance of measuring grip force. And as you can see, Nora and Sylvia here are lifting their cup of coffee and drinking from it while talking. And studies have shown that they modulate their grip force while doing this. So with the grip sensor, we can actually study this. In chapter 3 was the pendulum. Here, Rack is swinging on a pendulum, on a swing, and he tunes into the natural frequency of the system to help him swing higher and higher. If we didn't recognize the inherent dynamics of the swing, Rack would not be swinging because he would be swinging his legs at the wrong time. But we recognize what the object can do to help us as well. And then lastly, chapter 4 was manipulation of flexible and deformable objects. Still very hard on robotics, but here Vani is doing that with her shoelaces with a blindfold on. Here is the publication journey. What I showed in chapter 1 on the power law is already published in ICRA. We do have a follow-up to it in preparation as well. Chapter 4, the human-inspired control to move a whip, is published in BioRob. The grip sensor has been submitted, as I said, around a month and a half ago. The pendulum swinging is something Helen and I are working on, and close to being ready to submit. And then the last one was the robot manipulation, which is proposed because I only have one video so far of a robot kind of hitting a target.
Well, the work with Helen is ready to submit. That is an exaggeration.
Ready to collect.
Yes, that's much closer.
We've collected, but yeah, especially with the grip sensor, we're still needing to collect. I think there's some stuff written. So okay. So acknowledgements. Of course, I want to thank my PhD advisor, Professor Sternot, for her support all these years. My committee members, thank you all for waking up early and taking time to do this. Want to thank my lab mates. They all know that, like, and like we always work together, so they know that my work would not be possible without all their help. Especially thanking Alexei, Rack, and Helen, who were co-authors on the works that I showed. The grip sensor work would not be possible without Dr. Jim Papadopoulos' help. I've been working with Jim for the past 5 years, and yeah, every time I talk with him, I learn something new, and the grip sensor would not be possible without him. And lastly, I want to thank Mohsen and Reza, who were in the lab and are not here anymore, so they're not in the picture, but they helped me with my projects. And lastly, our funding sources. Thank you.